Welcome back. In the last video, I explained briefly the difference between the effect on the boundary conditions on the elastic compliance. And we said there's an elastic compliance with free stress. There's an elastic compliance related with constant electric field, and there's elastic compliance related with uh, open circuit or constant dielectric displacement. So the reason, and this is open circuit. This is closed circuit, and this is open. This has no electrical energy. This has electrical energy, and this is electrical energy due to an applied force. Due to applied force. So if you apply a force on the material, this would be SD. This is how stiff we would feel the material to be. And this is, let's see, we have electrodes, and we attach it like this. This is SE because it is less. It's less stiff. It's more compliant. So because SE is more compliant than SD, it's larger. So SE is greater than SD. Even though if we were going to say Young's modulus, the Young's modulus is greater. But in piezo realm, we like to talk about, the compliance instead of the Young's modulus. So the next thing I'll speak about is why are these subscripts this? Okay, this is open circuit. This is closed circuit. We understand that. This is open circuit. But why do you have a D there and why do you have an E there? So what the E represents, E superscript, means constant electric field. So constant electric field basically means any way that the electrodes are somehow connected to each other. So if the electrodes are connected to each other anyway, then there will be then you'll be using SE. So for example, I said the first case where we had the electrodes literally connected to each other with a wire. That is SE. But also, we need to consider that when these electrodes are attached to a voltage source, they're also connected. See, there's a sustained potential across this material. There's a sustained electric field. We are controlling the electric field. So basically, SE means that we are controlling the electric field under, you can say, the elastic compliance measured under a controlled electric field. And now when we talk about SD, this D superscript refers to constant dielectric field. So if we take the piezoelectric material, or rather let's look at the sensor equation, where we have D is equaling D equals the permittivity times the electric field plus D stress, and in this case the dielectric field is 0. So if 0 equals E, so the constant dielectric displacement means that there's no charge on the surface. There's no charge on the surface, instigated this dx, so that's obviously a dielectric field. Basically, it's D with a controlled. See, if we're applying basically controlled SD, it's measured under a controlled dielectric displacement. So what this means is that we are by changing the stress, we are directly changing the dielectric displacement of the material, because we're not applying any electric field. So this means essentially that within the material. Okay, here we go. This means within the material there's a constant dielectric displacement. And now I'll explain what that means. Within the material there's a constant dielectric displacement. So originally we had this equation, right? D epsilon plus dx. And I told you for open circuit, basically we have this material, we're pulling on it, and then we're getting charges on the top, charges on the bottom. I told you that for open circuit we have this, D equals dx. Well, that's not the entire truth here. This is what we're seeing from an outward perspective when we're considering these charges. This is how these charges are enacted. But when we are considering inside the material, see these charges, what do? Think about it again. Think about this. Charges, they create electric fields. So from positive to negative, electric field flows down. Okay. In the material, this electric field exists in the material due to the stress. So we're applying some stress from forces. We're causing an electric field to occur. So, and actually what happens is that how big is this electric field? This electric field is as big as the charge is created. So let's just call this D external equals dx. Okay. And basically D external equals dx. What is the electric field caused because of this? Well, we know that this is charge Q per area equals D, which is force. We don't want force, but we can stick with that. Force per area. Say force, or let's just keep it as stress. So basically, the amount of charge created is dxa. Okay, and how do you relate charge and electric field? Well, the electric field created because of a charge. Well, let's just take a look at Q equals CV. Okay, so Q over C equals V. Q over area, dielectric permittivity, thickness equals electric field times the height. Well, the height is also the length, also the thickness. So this is the main thing, length. So basically, we have Q L A E equals E L. These L's cancel out. So the electric field is equal to the Q A E. And now we gotta look up what's the definition of Q. Well, we had this right here. Q equals dxa. dx a e equals e, these cancel, dx over epsilon equals e. This is nice. This is a nice equation right here. This is cool, man. If you don't think it's cool, then you are not cool. Let's continue next time.